there was little thing available that about the application of sciences. So he tried to induct that kind of practices as ISC Bangalore. And whatever ISC Bangalore nowadays, that is maybe Professor Satish Dhawan has a lot of contribution for that. Now, now here that our is this is a small journey for us because we have been working with hydrogen. We know that hydrogen is a very noble fuel. The reason is that when hydrogen burn, it produces water only. It is no way polluting the atmosphere, and not only that that it can be used not only as a fuel but also to produce several other products. So, it has tremendous potentiality as per use is concerned. Now, before I start my presentation, let me share some thought of this Swami Vivekananda that what he told that all power is within you. You can do anything and everything. Those who are very young, but they should follow this because that this is the strength. What Swamiji told that if there is the will, there is a way. So if you have this will force very strong, then you can get your job done. That we started our hydrogen research work more than 20 years before, and I can remember one professor from USA. He was my family friend. Then every time whenever he visited India, he insisted me why I am not doing something on hydrogen. So that at that time I was mostly concentrating on ethanol and methane, this fermentation process. But after several years, my wife told me that since this professor asking you to explore this area, why don't you do little bit on that? Then I called my student one day and asked him that let us do something on hydrogen. So what we did, we initially we did some kind of literature survey, what we usually do for all the students, and try to find out that what was the present status of biohydrogen production as per the world is concerned. And what we have found that time, if you see the history of hydrogen, biohydrogen production is very interesting. I just show you the history. Now, scientists they started thinking that from water, algae can degrade the water and produces hydrogen. Then earth contain two-thirds of water. The scientists thought that if we can degrade, if we can produce hydrogen from water, it can solve our energy problem. But that is how this biohydrogen research started. But when they started doing this, and they found that with hydrogen, but this not only the hydrogen is the product, some molecular oxygen also produced during this hydrogen generation process, and this molecular oxygen acts as an inhibitor for the enzymes called iron hydrogenase, which is responsible for hydrogen production in the present in the algal cell. So whole research work comes to the standstill because scientists started thinking what to do now. Then they started thinking how to develop the oxygen tolerant mutant. So that research work still going on. But at the same time that we try to explore that since more emphasis has been given on the dark ferment on the photo fermentation process, or algal fermentation process, let us explore the other processes. So we have found that dark fermentation basically, that dark fermentation means the bacteria can not only work in presence of light, but in absence of light also it can grow. And if they grow in both the conditions, then hydrogen can produce throughout the day. But in case of photofermentation process, as long as light is available, then the hydrogen production takes place. So that is the limitations that we have. So I asked my student, why don't you explore this dark fermentation process. So this is a very big journey, and that how, and I want to share with you how we transferred the knowledge from the lab scale to the pilot scale. So so let me start with the current major issues that we have. That we have the global warming, as we know, and this is mostly due to the carbon dioxide which emitted to the atmosphere. It causes the greenhouse gases. Yesterday, Mr. Dr. Mitra was talking about this that Paris Convention, that we have a mandate that we should maintain the carbon dioxide concentration in the atmosphere constant, because that is the because so that global warming can be checked. So this is a great concern, and India has a commitment for that. So this is a great issue as per because if the temperature of the earth increases, then ice present in the northern the sphere of the world, that ice will be melted and sea level will goes up. And if sea level comes up, then we know some of the European countries, they are almost at the sea level, so they will go under the water. So it is a great concern of the world. Then then we have, due to rapid industrialization and urbanization, we have the energy crisis, because lot of energy demand keep on increasing, and most of the energy demand we are fulfilling on the fossil fuel. And we find, I shall give you the picture, that after say 100 or 150 years, most of the fossil fuel will be exhausted. Then there will be there will be a there will be a lot of demand for other energy sources. So that is the major concern nowadays. Now another is the waste management, and this particular webinar, that is the waste to energy. The waste is a great concern to the world, because it damage our atmosphere to a great extent, because we have, I can give you that example of the COVID-19 situation. And that is you can understand what kind of damage it can cause. So that we should be very careful about the waste disposal, so that that we can check kind of contamination of the water stream or atmosphere that we have. We have several environmental destruction, because we are deforestation, that also causes that drastically reduce oxygen concentration of the atmosphere and increasing the carbon dioxide. Then pollution, we have, as the time increases, number of vehicles also increases to a great extent due to rapid industrialization and urbanization. So that causes the massive pollution problem. Then fossil fuel depletion is a great concern, just I pointed out. Now, above all, there is another problem with the human population, that also increases day by day. So this is a great concern. All this is the present concern we have. Now, as far energy evolution is concerned, that we have two different sources. One is called non-renewable energy source, another is the renewable energy source. Now, these non-renewable things, that mean oil, coal, natural gas, and nuclear, they have a limited reserve, and that will be exhausted very soon. But as per wind, geothermal, water, biomass, and solar is concerned, that remain with us. And today I will be concentrating much more on the biomass rather than these other things that we have. Now this is the world energy source we have, that we have renewable non-variables, we have renewable variables, and non-renewable non-variables. We have, you can see that different sources we have. And most exciting thing is that the solar energy that we have in the earth, that is that power, that availability is 23,000 terawatt. 1 terawatt is equal to 10 to the power 12 watt. So that our see that our world consumption is 16 terawatt. You see that that the solar energy It is a huge amount, that is 23,000 terawatt, and our world consumption is 16 terawatt only. So you know that a fraction of solar energy, if we can utilize properly, then we can solve our energy crisis. Now, other renewable energy source, tide, it is from, if we use the tide of the sea, we can generate zero point 0.3 terawatt wave, 0.222 terawatt geothermal, 0.324 terawatt hydro is 3 to 4 terawatt, biomass 2 to 6 terawatt, wind is 25 to 75 terawatts. Besides that, you see that coal, that we have a storage of 900 terawatt, uranium 90 to 300 terawatt, oil is 240 terawatts, and natural gas is 214 terawatts. Now here is the world energy production by fuel. This record we get this results 2017, 3 years back. So this was the situation 3 years back. So you can see here, if you go through this, you will find most of the energy we consume from the oil. Then comes the coal, and then we have this natural gas, then other sources. 10% we tap from the biofuel and water. Now yesterday, some speaker was telling that we are targeting that 2030, that will be targeting the 40%, that biofuel. We want to generate the energy demand. The 40% of energy demand can be fulfilled through the biofuel. That was the target that we have. Now this is the this is little bit old table, that figure that we have, that that it was fine that production and demand, that is like this. So that time it was predicted that so this was little bit curve was not right actually, because this will be little bit this side. So it will be fine that up to 2020 or maybe 2030, that production and demand will go with the side by side. But after 30, the energy production will decrease from the fossil fuel, but energy demand keep on increasing. So as it increases, so naturally we require the energy from some other sources. Now, let me tell you that what is the fuel usage that we have. And if you look at our civilization, that we consider wood as a source of energy, and that is our starting point of our civilization. And then we use the animal fat as a source of energy, then coal, then petroleum, then propane, then natural gas, and after that is hydrogen and fuel cells. Now, why I am showing this, because if you consider the hydrogen and fuel cell can be operated with the help of hydrogen. And this is kind of hydrogen we are converted to electrical energy. So this is 100% free from the environmental pollution problem. So it is, so that so since we are stepping into this hydrogen and fuel cell, that means we are stepping into a particular era where their pollution should be as low as possible. That is why the importance of this fuel cell and hydrogen is coming up day by day. Now, why the hydrogen plays important role? There is 4 different reasons. One is the high energy content, no greenhouse gas emission, because when it burns, it produces only water. Easy transportation. You know that all kind of energy conversion processes, why we do? Because I can give a very simple example. Suppose if you want to convert some kind of lignocellulosic material to hydrogen. So in a lignocellulosic material, if you burn, it will get the heat energy. So why again unnecessarily the lignocellulosic material you can convert to hydrogen or other fuel like ethanol or methane? Why? The reason is that the gas and liquid is very easy to transport, because you can transport in the form of pipeline. But solid material is very difficult to transport. So transportation required lot of incurred lot of expenditure. So that is, and not only that, the fuel conversion efficiency. Suppose you want to use gas as a fuel or liquid as a fuel, then that conversion efficiency is much high as compared to the solid fuel. So this is the couple of reasons why we go for this conversion process, and can be produced from the waste material. Waste material, if we use it, it serves the two purposes, both with the bioremediation as well as the energy generation. Now, hydrogen has, I told you, it has several use. It can use for running the buses. It can use for car. Lot of car nowadays can be is operated with the help of hydrogen gas. Then the hydrogen powered train engine also there. Water taxi also there. Then space vehicles. Space vehicles, we use this for very longer period of time. You might be knowing that the electricity I told you just now in the fuel cell can be used for the generation of electricity. So that the electricity generation that usually takes place with the help of hydrogen. So in the space launcher, the space station vehicles, it is used for longer period of time. Then it has some domestic use and the industrial use, because a lot of industry they use hydrogen as very important chemical feedstock. Now, this is in India. As far India is concerned, recently that Tata they have they manufactured one. They made several buses. This is the Tata Hydrogen Fuel Cell bus. This has been 100% that prepared in India. So this is already done as far the Tata is concerned. So this is already on the in the road now. Now here there is another bus you can see. This is the transportation bus that is in Sweden, because in Sweden at the top you can see that it is biogas bus. When a biogas, we know it contains methane, and the methane they use as a fuel for running the buses. You can see that that is already in, I told you yesterday that CNG, that compressed natural gas, is largely used in Delhi and other part of India as a fuel in the automobile sector. The reason is that in the CNG or compressed natural gas, we have methane, and methane is the lowest hydrocarbon. And when you use the lowest hydrocarbon, there is no possibility of generation of carbon particles in the atmosphere. So, any kind of fog problem due to this fuel can be avoided if you use the CNG. That is the major concern that we have. Now, the hydrogen can be produced that by two different ways. One is called biohydrogen, another we have one is biological, another non-biological. Now, biological process, we have two types. One is called light dependent and the light independent. The light dependent means we have biophotolysis, where both cyanobacteria and algae, I told you before also that they participate in the reaction and produce hydrogen. And photofermentation process, where a different kind of waste material, particularly organic waste, organic that acid, or some kind of soluble carbohydrate can be easily converted to hydrogen. But that major problem I told you in case of biophotolysis, the major problem is that oxygen toxicity, molecular oxygen toxicity. And this photofermentation process, this major problem is that the pigment formation, because as the fermentation started, there are a lot of red pigment formation is there, and also some kind of cell mass formation is there that causes the light penetration problem. And since that growth of this photofermentative organism depends on the light energy, so as since it gives some kind of obstruction to the flow, or that is the penetration of the light, that is why that hydrogen production decreases. as the time passes on. So we concluded that these two processes, that biophotolysis and photofermentation process, because I had a project with that has been funded by Norwegian Foreign Ministry, and their main objective was that I told you that algae, just to find out that the potentiality of the algae for hydrogen production. So we have concluded that as such algae is not, no way it is good for hydrogen production, but algae can be used as a nutrient supplement for the dark fermentation process for the microorganism. I shall come back to that, and that can help for this dark fermentation process for the growth and metabolism of the organism. That is there, but these two processes, particularly biophotolysis and the photofermentation process, is no good for hydrogen production. And that, photo light independent process, we have dark fermentation, where so many different type of bacteria, both mesophile and thermophiles, they can work here. Now that in thermophiles has some advantages as compared to mesophiles. The reason is that thermophiles, they always act at a higher temperature, maybe above 60 degrees centigrade. As you know, at 60 degrees centigrade, most of the pathogens, they are killed. So naturally, when you use any kind of waste material for the hydrogen generation, so you don't have to sterilize that. Just you maintain the temperature at 60 degrees centigrade and use the thermophilic organism, you can produce hydrogen very fast. I can give a very typical example that distillery effluent is usually coming out from the factory at about 65 to 70 degrees centigrade. So if you can take that effluent directly to the fermenter, and you make the fermenter insulated, so you don't have to add additional energy to maintain the temperature. Automatically, the temperature can be maintained at 60 degrees centigrade, and you can put your thermophiles and you can produce hydrogen very fast. So this is the advantage of that. And but problem with these thermophiles is that mostly they are obligatory anaerobe. So if trace amount of oxygen present there, then the growth of the organism will be a problem. Otherwise, the mesophile or mesophilic organism, they're in that way they're better because they're mostly the facultative in nature. Even little oxygen, presence of oxygen will not affect their fermentation process. So this is the advantage of this process, and so it can be handled very easily. Another process we have, that is called microbial electrolysis process. I think Professor Dr. Venkat Mohan will be the next speaker for this after my presentation. We are also doing a lot of work. Our institute also done a lot of, other group also doing lots of work on that. And that microbial electrolysis is a kind of process through which this organic waste can be converted to the electricity. We consider this as a green fuel. Now, this is all about the biological process. Now, what is about the non-biological process? In non-biological process, we have steam reforming process, that where the methane can be used, and it can produce hydrogen, carbon monoxide and hydrogen. You can see it here, and then electrolysis of water largely used for the degradation of water to this hydrolysis water to hydrogen and oxygen. Then coal gasification, there is another process through which they can produce hydrogen, and another is the photocatalysis process. Lot of research group presently they are working on this area just to explore this photocatalysis process for the hydrogen production. Now, this is kind of a pictorial representation of biohydrogen production process, because what we want to show you, this is the industry, like thermal power station, they produce a lot of carbon dioxide, and this carbon dioxide we can fix in the form of algae, and this for the carbon dioxide can be utilized algae for their growth, and then this algae can be used as a substrate for the dark fermentation process and for the production of hydrogen. Also that, we can use some kind of industrial waste material that also can be used in the dark fermentation process for the hydrogen production. This waste material can be used in the microbial fuel cell for the electrolysis generation, and microbial electron capture cell that can be used for the hydrogen generation. This hydrogen that, finally it can be used in the fuel cell for the generation of electricity. So, this is the kind of, very compact way of presenting the whole scenario that we have, how best we can use this biohydrogen production process, and by utilizing different waste material generated both different industries, both in the form of liquid, in the form of gas. Now let us see that the dark fermentation process that we have, that that we have this is the efficient hydrogen production operate at ambient temperature and pressure. If you use the mesophile, they can operate at ambient, because we are in the tropical country. Our temperature is lies in between 30-35 degrees centigrade. So 35 degrees centigrade is very good for our organism for the growth and metabolism. Does not require light energy, easy for scale up and cost effective, and different waste can be utilized. This is the advantage of that. Now, if you look at that, how this hydrogen is formed, the glucose, we know this is the glycolytic pathway. This is how it produces the 2 moles of 1 mole of glucose converted to 2 moles of pyruvic acid. And this 2 mole of pyruvic acid can be converted to acetic acid, it can be converted to lactic acid, it can be converted to ethanol, it can be converted to butyric acid. Now, if it is converted to lactic acid, it will not produce any kind of hydrogen, but it will consume that 2 moles of NADH. Because this NADH is very good material for the hydrogen production, because the NADH contributes, you can see it here, the NADH that can contribute the pyridoxine, the reduction and oxidase, they involve for this hydrogen generation process. So their lactate formation pathway, it will not give any hydrogen, but in addition, it will consume 2 moles of NADH, so that that overall the hydrogen production in the process will be reduced to a great extent. Similar thing happens if the ethanol production takes place, where 4 moles of NADH2 that will be converted to NADH, and then also we'll be using this NADH for the hydrogen generation. But these two pathway appears to be the better, because if it follows the acetate formation pathway, it produces 4 moles of hydrogen, and if it follow this butyric acid pathway, it produces 2 moles of hydrogen. So so our target, because when we handle the particular process, we always target that how we can switch over this fermentation process towards the acetate fermentation process. So what we can do, we can develop a mutant which can close this particular acetate lactate formation and the ethanol formation, so that we can save a lot of NADH, and if we can direct it to the acetate pathway, then we can improve the hydrogen production of the system to a great extent. Now another important issue is that when I shall show you the whole journey, that what we have done and what is the present status, and what we have observed, that hydrogen production, that process, the energy generation by the hydrogen production process is not very high. It might be around 30% on the 30 to 33% on the basis of substrate energy. But still, lot of, because metabolites formed after the hydrogen formation is the volatile fatty acid. You know that the spent media that forms after this acid fermentation process is the volatile fatty acid, and this volatile fatty acid is a very good raw materials for methanol, for biomethane product methanation process, where the volatile fatty acid means acetic acid, butyric acid, propionic acid. This acid can be converted to methane and carbon dioxide if you pass through the biomethanation or the anaerobic digestion process. And the next is that this acid also used as a substrate for the acetone butanol fermentation process. Now there, this is called acid formation, and this is called solvent genesis. And solvent genesis means that the acid is converted to alcohol. So if you use this process, we can generate, because I can give a typical example. We have been working with Clostridium species just to produce hydrogen and butanol. Butanol is also very good fuel because it is better than ethanol, because butanol solubility of butanol in water is very less, but solubility of ethanol in water is very high. So naturally, that ethanol is hygroscopic in nature and butanol is not hygroscopic nature. And another thing is that butanol has the high calorific value, but ethanol has very low calorific value. So that is the problem that we have. So this is butanol is appears to be the better raw materials as compared to ethanol. Now, photofermentation process, this volatile fatty acid with the help of photofermentative bacteria, just now I was talking about, that can produce hydrogen and carbon dioxide. But at the same time, I told you, due to the pigmentation and the cell mass formation, light penetration is the problem. So performance of the reactor will go down as the time proceeds. Then we have bioelectrochemical system, where this organic acid can be converted to electricity and hydrogen, both we can. But when we use the electricity with the help of a microbial fuel cell, and when we want to generate the hydrogen, we use the microbial electron capture cell. Now here, the difference is that this is the natural process. Just you pass wastewater, it is automatically converted to electricity. But here, that you have to put some kind of additional voltage just to generate the hydrogen. So this is the difference between these two processes we have. And another is the microalgal cultivation system to produce the biodiesel, because some kind of cyanobacteria can use this organic acid as a substrate and produce kind of algae. And this algae, it contains good amount of lipid, and this lipid can be converted to biodiesel. Biodiesel is nothing but monomethyl ester. You might be knowing that monomethyl ester. Now, when you compare these all processes, that biomethanation, acetone butanol fermentation, photofermentation, bioelectrochemical system, and microalgal cultivation system, we find that biomethanation system is a well-established process, because that is already in practice both in the small scale and bigger scale. So that what we believe, that hydrogen production followed by methanation is the is the is the is the it has the brighter prospect in the year to come, and that is called biohydrogen process. Biohydrogen means biohydrogen followed by biomethanation process. So we have been working with this biohydrogen process. I just show you how the biohydrogen process is better as compared to this biohydrogen and the biomethanation process. Now, this is how we can point out that in case of this biomethanation process, that 1 mole of glucose is converted into 3 moles of carbon dioxide and 3 moles of methane. So if you calculate the maximum energy conversion efficiency with respect to glucose, it is 85%. And then in case of biohydrogen production process, just now we have seen that acetic acid pathway gives the better hydrogen yield, that is 4 moles of hydrogen. Now, if you calculate amount of heat generation, amount energy generation or energy recovery, it is about 34.2%. So it is so if you compare these two processes, obviously the biomethanation is better as compared to biohydrogen production. But I was discussing about the biohydrogen process. That means I was talking about the first is the hydrogen production, then followed by the methanation process. Now, if you do that, then total energy recovery will be 91%. So it is much better than either this biomethanation or biohydrogen production process. So what I want to point out that biohydrogen is because hydrogen, I shall show you that why hydrogen is required with methane, because we find that if we mix hydrogen with methane, the quality of the fuel that increased to a great extent. That is why that is called hythen. That is that has the tremendous potentiality in the automobile sector. Now this is the another representation that we have. This is the dark fermentation, and this is we have photofermentative process and the biomethanation process. Now you see that. So what I am saying that if you after carrying out the dark fermentation process, the volatile fatty acid, if you pass through the photofermentation process and biomethanation process, what kind of reaction you will be having? Now here, 2 moles of acetic acid can produce 8 moles of hydrogen in presence of light in the photofermentation process. But at the same time, I told you we have a lot of operational problem, and since we required light, we have some scaling up problem also there. When the biomethanation process is a very easy process that is operating for a very longer period of time, and this can be easily converted to methane and carbon dioxide. So what they pointed out that the lower hydrogen production rate in case of photofermentation process contain uptake hydrogenase enzyme. They can utilize the hydrogen for the growth and metabolism, so they decreases the hydrogen content in the gas, and high suspended solid and shading effect due to color, which results in poor light penetration. This is the major problem that we have. Now, in the biomethanation process, is advantageous because they require no need of light energy, can be produced from different organic waste, and large scale production is easier than the photobioreactor and will establish process. Now, this is how pictorially you can represent this process. The wastewater first comes to the dark fermentation process. It produces hydrogen and carbon dioxide. Then the spent acid that goes to this methanation process is produce methane and carbon dioxide. So this is another that how the degradation takes place. Initially, we have complex organic matter present in the waste material like polysaccharide, proteins, and lipids. This will be first hydrolyzed to monomers or oligomers, the sugar, amino acid, and long chain fatty acid, and then it produces some kind of volatile fatty acid. And during this volatile fatty acid formation, it produces hydrogen and carbon dioxide, and this volatile fatty acid finally converted to methane and carbon dioxide in the anaerobic digestion process. Now, if we look at the history of hydrogen production process, also very interesting. Hi. Hydrogen was first invented by the scientist whose name is Philip von Hohenheim. This is the hydrogen gas was first artificially synthesized by mixing metal with strong acid. In school, we have seen how hydrogen H2S can be produced when metal is react with the acid. So that was the how this hydrogen generation take place. Then Robert Boyle, in year 1971, the reaction between the iron fillings and that dilute acid, which results in the production of hydrogen, noted as fume, highly flammable. Now, Cavendish, that he recognized hydrogen as a discrete substance by identifying the gas from a metal acid reaction as a flammable air, and noted that gas produces from water when burned. Then Lavoisier, he named the element hydrogen. The hydrogen name comes as like the hydro stands for water, and gene stands for the creator. That hydrogen, that means hydro from water, since we are creating this hydrogen. We call it hydrogen. That this is hydros stands for water, and gen stands for creator. And then James Dewar, he was the first to liquefy the hydrogen and produce also the solid hydrogen. Now, as far biohydrogen is concerned, the history of biohydrogen is like this. The Heinz Gaffon, the scientist of University of Chicago, observed that green algae has the capability of to produce hydrogen instead of oxygen. And then they wake up that in a California University observed the produce hydrogen from the algae by sulfur deprived media. Then my friend that John Benjamin, he published the paper in Nature Biotechnology, mentioning that biohydrogen production deserves serious funding. The history of biohydrogen process is like this: that in 1989, the term hydrogen was first used by Frank Lynch and the Rogers Marmaro, and hydrogen was developed in the laboratory of a company called Hydrogen Component In. This is HCl. And then the technology patented in 1992 in USA, and first hydrogen station was built up and opened. And the idea of biological hydrogen production was first proposed by John Benjamin in 1998. In 2003, the first study of biohydrogen from the waste sludge was published by the Wang et al. And then 2004, the first pilot plant demonstration of hydrogen methane production from kitchen waste was established in Japan. Now, I told you that the hydrogen has several properties, that wide flammability range and more than 6 times wider than methane, long ignition energy, about 20 times less than low ignition energy, 20 times less than the methane, then high flame velocity, 8 times faster than methane. That is why we mix with CNG, 7% hydrogen we mix just to improve the quality of the fuel, and powerful reducing agent and combustion stimulant in the chemical industries. Now, as far waste is concerned, and this particular webinar is one important part is the waste. So if we consider the waste, it can be categorized, classified into two types. One is called solid waste, another we have liquid waste. Now, solid waste, we have municipal waste, we have agricultural waste, we have industrial solid waste. Now, municipal solid waste, we have organic litters, household waste, and swales. And agriculture waste, we have algal biomass, we have energy crops, we have food crops, and the lignocellulosic biomass. Industrial solid waste, we have food processing industrial waste, dairy industrial waste, and the agro-industrial waste. Now, liquid waste, we have two categories. One is the industrial wastewater and the domestic wastewater. Industrial wastewater, we have distillery effluent, we have paper mill effluent, we have starchy wastewater, we have pharmaceutical wastewater. The different type of industrial wastewater is there. And domestic wastewater we can get from canteen waste, household wastewater, and starchy wastewater. So, the major issue is that biomass, the boon to the society, because biomass can be considered as one of the key renewable resource for the future for small and large scale level. So that is the beauty of this process. When we talk about the hydrogen or methane production, this biomass can be used not only in the small scale, but also can be used in the bigger scale. It has already supplied 14% of the world primary energy consumption. This is already supplied, because previously I showed you 10%, that is in the year 2017. Now it has been increased to 14%. And on average, the biomass produced 38% of primary energy in the developing country like India, and 90% in some country. Because more is the poorer nation, that the use of this biomass and the energy source will be more and more. Now, let me share my roadmap that is on this hydrogen production process. I have the Google Scholar H index is 53 and I10 index is 142. And I'm glad to report you that our review paper that hydrogen production from biological processes is Survey of Literature, which published 2001. This is published by written by myself and the Veziroglu, who is considered as the father of hydrogen in the world, because his name was nominated for the Nobel Prize 3 times, but unfortunately it didn't work. But he is a very famous scientist. And then we slowly we start. I told you we started this work 20 years, more than 20 years before, and then slowly we try to generate. We identify one bacteria called Enterobacter cloacae IITBT08, which can produce hydrogen very fast. Now initially this organism has it was reported much. They reported the other Enterobacter species, not Enterobacter cloacae. But that is why we got tremendous that opposition from the scientists just to justify how the Enterobacter cloacae can produce hydrogen. So that later on we try to do some kind of molecular biology study, and not only that, this particular organism, since it is a new organism, and this organism we we do the whole genomic study, and that has been already reported. And like this, and we develop the continuous process, and then I want to tell that a very interesting thing, that decreasing partial pressure that increase the hydrogen production process. That I shall discuss later on, that how the hydrogen partial pressure increase the hydrogen production process. Then another interesting observation that we found, that we try to isolate the bacteria from different sources like sewage sludge, like high oil containing soil, and try to find out their potentiality for hydrogen production. Then we try to use that organism to in a combination, just to find out if we use together whether it will improve the hydrogen production or not. And you'll be glad, you'll be surprised to know when we try to find out that how this organism work, we find that that it is very much substrate specific. Because suppose we are isolated the bacteria from the sewage sludge, and when we use the 3-4 organisms together, we find that organism, that bacillus coagulans that we isolated from the sewage sludge, that growing very fast as compared to other organisms. Like in the high oil containing soil, if we use, then we find that Citrobacter friendly that grow very fast as compared to other organisms. So this is very substrate specific. Then we do some genomic and proteomic approach for the biohydrogen production process. Then we published several papers on hydrogen. Recently, our process has been commercialized, because commercialization has been taken by the industry for the commercialization of this process, and we published a paper on that. So anybody interested that how we have done that, is just they can go through this paper and know the things in details. So biohydrogen, I was telling that this will be the fuel for the future. We have written one book, Biohydrogen Fuel for the Future. This has been published by Pan Transport Publishing Company, and this is in Singapore and marketed by CRC Press. And this is the first book in the world. And then we have several papers, research paper also, just to justify how the biohydrogen process is suitable for this hydrogen generation. Now, this Let me share some of our work that we have in our lab. That this is the Enterobacter cloacae, how it looks. This is gram-negative rod-shaped organism, facultative anaerobe, and this follows the mixed acid fermentation process, and it produces hydrogen under anaerobic conditions. And then we there is a we try to isolate the organism, because I told you the Bacillus coagulant and the Citrobacter friendly. Bacillus coagulant we isolated from the Swiss sludge, and Citrobacter friendly we isolated from the high oil containing soil. This also produce hydrogen very good. But recently we have come across this other type of bacteria, and I told you in the anaerobic digestion process usually carried out by the two group of microflora. One is called acidogens, another is called methanogens. Now these acidogens is actually that we try to work with these acidogens and try to find out how their potentiality for hydrogen production. And we found they have very good potentiality. They are almost same as that of Enterobacter cloacae. The difference is that suppose if we want to use the Enterobacter cloacae, you have to maintain the sterility of the process since it is a single organism. But when we are using the mesophilic, that mixed consortia, we don't have to use the sterile condition. We can use the as it is, the waste as it is, we can use for the hydrogen generation. The same thing happens to the thermophilic, mixed consortia that we isolated from the hot spring, and you know that this also find very good potentiality for the hydrogen production. So. So this is the comparative the table that how the different organisms are comparable with our Enterobacter cloacae. We find that our organism is comparatively quite good, because in the highest that double mutant of Enterobacter cloacae can produce 3.8 moles of hydrogen per mole of glucose. So it is the very high amount. And you know that theoretically it is maximum about 4. We almost reached to the theoretical value. And this is kind of experimental condition setup that we have. This is the control module of the fermenter. This is New Brunswick fermenter. This is the 10-liter fermenters. This is the gas collector that we have. We collected by using 5% the saline water with the acidified saline water, so that the carbon dioxide solubility can be reduced, and then and this fermenter we use, and we try to establish the fact that how our organism can utilize the different carbon source. We find it can degrade cellulose, it can degrade arabinose, it can degrade fructose, maltose, potato starch, CMC cellulose, xylose, dextrose, and sucrose. Now, what does it indicate? What it indicates that this organism has the capability for utilizing the different carbon sources. So, if you come back to the waste material contains the different type of organic material, and several type of carbohydrate it may contain. So that is why this organism is very good for utilizing different type of waste material. And we observed the cellulose and the sucrose appears to be the best substrate for the hydrogen production. You can see the cellulose, we have 5.4 moles of hydrogen per mole of cellulose, and sucrose, we have 6 moles of hydrogen per mole of sucrose. Now here we have very interesting observation that we have, that this is the pH profile of this fermentation process. Now we use both the condition. We have to use the anaerobic condition, aerobic condition, and anaerobic condition. Now, if we use the aerobic conditions, the pH will decrease like this, and it will go similar as your anaerobic process. And then after 10 hours of fermentation, pH will increase in case of aerobic fermentation process. But the anaerobic fermentation process, the pH will keep on decreasing. because we can get, but this organism can produce the hydrogen only under anaerobic condition, not under aerobic conditions. So aerobic condition, it can produce cell mass, and there the pH will increase after 10 hours of fermentation. This kind of pH profile we obtain, and then we try to find out that what pH is suitable for the hydrogen production. We find little bit acidic pH, maybe 6.5 is suitable for this hydrogen production. And then you know that batch system is no good for hydrogen production. So we try to have the continuous system. Now question comes, those who are using the CSTR, continuous start tank reactor, the major problem of continuous start tank reactor is the cell mass wasting from the reactor. So if the cell mass that is wasting from the reactor is equal to the cell mass growth in the system, then what will happen? If the cell mass wasting is more as compared to cell mass growth, the cell mass concentration will decrease with respect to time, and the performance of the reactor will go down. This is the major disadvantage of using continuous start tank reactor. Now, this problem can be overcome by using the immobilized system. So you can see here, that is the immobilized system that we have. Sorry. So I want to say here, you can see that this is what I want to say. This is called rhomboidal reactor, or that you can see convergent and divergent. Can you see it here? Now here we have this solid matrix, and in the solid matrix we fix the cell on the solid matrix surface, and then we pass the substrate from through this, and we collected the gas with the help of gases, that water displacement technique. Now here that here that what is happening, that uh, that that this, since this is a kind of packed bed reactor, and it is a gas generating system, the gas will hold, because that gas will hold in between the solid matrix. So there will be, if gas present inside the solid matrix, then working volume of the reactor will go down. So that is the major issue of this problem of this particular reactor. But advantage of this process is that since we have convergent, here we have convergent and here we have divergent. Now as the convergence, the bubble will, coalitions of the bubble here will take place, and then when you have big bubble, you try to go up like this very fast. So there will be some kind of hesitation is there, kind of buoyancy force is there. So that buoyancy force reduce the gas holdup problem to some extent. And we find, by using this technique, we find that it improved the gas production to some extent. Now here I want to point out, just a minute. Can I remove that? I don't know, it has come from other side. Okay, no problem. So that what I want to point out, that suppose you have three different solid matrix. We have SMA, SM2, SMB, and SMC, and these all are lignocellulosic material. And when you use that, you find that density of the packing material is like this. There's a gram of solid matrix per liter of the reactor, and say the cell loading is like this. So we find that in case of SMC, the cell loading is more. It is 0.44 gram of cell per gram of support, and that is why this particular solid matrix gives the better results. Now, when we use the different type of reactor, like this is called tubular reactor. Tubular reactor means it's just like a tube, and this is the TAPA reactor, that you can see how the TAPA reactor looks. This is the rhomboidal reactor. We have convergent and divergent. So if you use that, then you see that that at the same dilution rate, if you use the gas production increases in case of raw material reaction, and your gas holdup problem will be less in case of raw material reaction reactor as compared to tubular and tapered reactor. That is why our hydrogen production increased by 13.6%. And this is the kind of dilution rate, how it affects the high rate of hydrogen production. And we have observed that 3.6 that milliliter per minute or the dilution rate 0.545 is most suitable for the hydrogen production, with substrate conversion efficiency is about 45%. And this is kind of profile of the hydrogen production and the cell mass concentration that we have in the system with respect to dilution rate. But most interesting thing is here that if you look at, because cells when remain in suspension and cells when are immobilized, it is usually observed when you fix the cell on the solid matrix, the generation time increases. But in our case, we find little decrease in the generation time take place, because the the difference between the two peaks is we considered as the generation time. And how we define the generation time? Generation time is the time required for the cell division, because time required for the how much time required for the cell division. So this we find in case of suspended cells, it is little bit high as compared to immobilized cells, which is little bit different as compared to the other system. Now this is the solid matrix. You can see this is the kind of fiber that we have, and here you can see how the cells they can grow on the surface of the fiber, and you can see here how cells are coming out, or what we call oozes out from the surface. You can see the how cells are coming out from the surface of the solid matrix. Now, I was talking about the effect of partial pressure on the hydrogen production. And this is the Le Chatelier principles, the equilibrium constant. This is the reaction, and this is the reversible reaction. And the reversible reaction, we have equilibrium constant. And this reaction, we can represent it like this. And here, you see that our gas is hydrogen and carbon dioxide. Now, hydrogen and carbon dioxide, if you applied vacuum, then you can take it out. And if you can take it out, then what will happen? The numerator will decrease. So more substrate will be converted to hydrogen and carbon dioxide to make Kc constant. So this is how, through negative pressure, that improves the hydrogen production. And we find 380 to 760 millimeter mercury pressure that is good for the hydrogen generation system. So you can see that 380, that we get the maximum hydrogen production of 3.9 moles of hydrogen per mole of glucose, and whereas 760 we got 1.9. So by when we applied the reduction of this partial pressure of hydrogen, that improved the hydrogen production to a great extent. This is another table that we have. Now, when this system we use just to find out different kinetic constants, because we have several kinetic constants, and these kinetic constants are very useful for scaling up of the process. We have calculated what is the maximum specific growth, what is the saturation constant, what is the true growth yield, what is the maintenance coefficient, what is the growth associated coefficient. All this is the different equation we have. This is the Gompertz equation, this is the Ludeking-Piret model, this is Monod equation, and this is the part model. So this is how we can do that. We can this is the kind of simulation curve we try to find out the suitability of this particular equation. And this is kind of comparison that we use different the organism different. We use Interbacter clocky, we have used the immobilized mixed culture, we use thermophilic mixed culture, and co-culture we use with Enterobacter clostridium, just Citrobacter friendly. So we try to find out that how it is they are comparable with each other, and this gives some kind of comparative study how different system, and we find that continuous system appears to be better as compared to batch process. Now let me come back to very interesting that thing that we observed during our research work, and particularly for the students, I want to share this knowledge, because you know that when you use any kind of waste material for any kind of fermentation process, the waste material is the waste of the particular process. So naturally, it passes through the different state of this process, and in process, we the material loses nutritional value. So naturally, the waste material, most of the waste material generated by the industry, as such, they are not suitable for the fermentation process. And for that, what you have to do, you have to put some kind of nutrient. So sometimes we add some kind of yeast extract, malt extract, or other trace nutrient, which can improve this growth and metabolism of the organism. But those are very costly. Now, what we try to do, we use some kind of bee oil cake. They are the waste material from oil producing industry like sesame oil. We have this rice bran. We have soybean, then coconut, groundnut, coconut, and mustard oil cake. That's why you know that the different this waste we can use as a nutrient supplement for distillery effluent, starchy wastewater, lignocellulosic biomass, or the cane molasses. And when you use together, they produce hydrogen quite significant amount. Now, this is the photo fermentation I was talking. They produce the red pigment. You can see the red color here. And this is the biophotolysis process where we use the algae, and they have the green pigment. You can see it here. How the this is the rocking the flatbed reactor. This we design and fabricated. We designed by ourselves and fabricated in Norway. And but the dark fermentation process is mostly used. And this is we make a comparative study. Suppose this is a cane molasses, this is a distillery effluent, this is starchy wastewater. Now, if you don't use any kind of nutrient supplement, then how is the your hydrogen the yield? Hydrogen yield here is 5.1 moles of hydrogen per kg of CO2 removed. But as soon as you add some kind of yeast extract to cane molasses, then it is 9.8 moles of hydrogen per kg of CO2 removed. But if you use the chemical substitute like chemical nitrogen source like diammonium phosphate, then it is 8.6. It is a little bit less in compared to that. But when we use the groundnut dual cake, then we get 11.6. So what I want to point out, not only groundnut dual cake, not only it is cheap, it has better nutrient value as compared to yeast extract, as per our process is concerned. Now, in case of distillery effluent, also we find that in case of yeast extract is 7.5, and in case of groundnut dual cake is 7.4. Almost they are close to each other. Now, in case of starchy wastewater, in case of they have yeast extract, this is the 6, and whereas the groundnut dual cake is 7.6, is better as compared to yeast extract. So this is how we can replace the conventional the nutrient supplement, what we call yeast extract, in this particular fermentation process. Now, this is kind of the material analysis of the process. This is a zero point 0.5 liter reactor. You can see it here, 0.5 liter reactor. Then this is 0.5 liter reactor, and this is cane molasses, groundnut dual cake 1 kg, and 36 or 34.7 gram COD goes in the form of hydrogen. But most of the thing, this thing comes in the form of acid, the acetic acid, butyric acid, and ethanol, then biomass, and also effluent. And then Then this is again we use this is by just by replace the de-oil cake by yeast extract. What is the material balance? We find little improvement of the hydrogen production, and this is kind of 20-liter reactor we develop in our lab. You can see this is custom made 20-liter reactor, and this is the vacuum recycler we develop by ourselves. The detailed diagram is given here, and we apply the vacuum in between 380 to 760 millimeter of mercury, and we find very good hydrogen production. That this is a gas collector, this is the vacuum recycler, this is the reactor that we have, and this is the watch glass through which you can see the level of the liquid. And this is the 20-liter reactor that operation, the material analysis of the process. This is if 1 kg COD you put, you have 80.8. Previously, you have seen 50 gram. Now it has improved to 80.8 gram, about 81 gram. So in the continuous system, we have this improved the hydrogen production to a great extent. And this is the kind of summary of this particular work that we have. That we have the intervector clocking. When we use the cane molasses and yeast extract, we have 4.2 moles of hydrogen per kg of COD removed. Then if we use the de-oil cake is 5.2. Then when we use cane molasses and yeast extract in the backbed reactor is double. And when we use the continuous system, and then it is about 12.7. So it increased to a great extent. Now this result, what we obtained, that has been transformed to the pilot scale, and this pilot scale has been located at IIT Delhi. And this is the 10,000 liter reactor. You can see it here. This is the 10,000 liter reactor, and this is the two reactors. This is 3,000 liters and 3,000. This is considered as the feed tank. That is the material, that media we prepared in this tank we transfer to the, this is production fermented. And this is the 50-liter reactor. This is 500-liter reactor. This is used for the preparation of the inoculum. But initially we prepared the culture in the 5-liter reactor, then 5 liter conical flux in the lab, and from 5 liter we transfer to the 50 liter, and under aseptic conditions. And then we find out that that when the rate of hydrogen production is maximum, then we transfer this culture to the 500-liter reactor. And when here the hydrogen production is maximum, then we take 4.5 cubic meter of the feed of the media in the 10 cubic meter reactor, and 500 liter of this inoculum we add. And when the rate of the hydrogen production is maximum, then we fill it up with additional 5 cubic meter of the media. So we get the hydrogen production. So so this is the result that we have. This is the performance of the 50-liter reactor. I told you this is a 50-liter reactor. We have the total gas production is about 91.85 liters. This is, you can see, this is the 7 hours of fermentation. We get this much of hydrogen production. Then this is 500-liter reactor. We get about 580 liters of hydrogen production after 5 years. 5 hours, you can see that 5 hours we can produce this much of hydrogen production. And then finally we transferred this to this reactor, and then our gas production slowly with respect to time is keep on increasing like this. This is kind of material analysis of this process. We have, if we take 170 kg of COD, out of that 54.734 kg of this COD can be recovered in the form of hydrogen, and we get a significant amount of acetate, butyric acid, and ethanol and propionic acid in the in the fermented broth, and in addition to biomass and effluent. This is the another energy analysis that we have, you can see. And this is the final thing that I want to share with you, that that total energy recovery that we get in the system, we calculate in two ways. One is in terms of substrate added, it is 21.6%, and if we use the consider the substrate removed, it is 37.9%. So this process has been taken by Dhampur Sugar Mills Limited, that is in Dhampur, UP. They have taken this process, and I request all the students. We have a website, www.bios2iitkgp.in. If you visit the website, you can find out the operation of the 10 cubic meter reactor. You can find out how we operate the system. You can get the idea that how the pilot pen can be operated. And this is the net energy gain of this process. We try to do some kind of analysis of the energy analysis of the process, and we find as the temperature increases, that the energy gain will be more and more. But since we are in the tropical country, our ambient temperature close to 35 degrees centigrade, so our energy gain is high as compared to the Western country where the ambient temperature is quite low. So this process, I want to say that is better if we can be operated in India as compared to Western country. Now this is the summarized table. Now you can see the cumulative hydrogen production when we work with the lab. This is we get in the 0.002 cubic meter, where hydrogen production is 2.6 liter per liter of the reactor, and when we use the 0.05 cubic meter reactor, then we get 2.9, but when we get the 10 cubic meter here, 7.6. So as what I want to stress here, as we scale up, our hydrogen production increases, but much more favorable in the higher scale as compared to the lower scale. And this is another thing I want to just study, that want to share with you, that the spent media that we obtain from the dark fermentation process, we try to find out how it is suitable for the methane generation process. We work with three different culture. One is spent media formed by using Enterobacter cloacae, spent media from co-culture, spent media from acidogenic mixed consortia, and we find the acidogenic mixed consortia gave the better methane production as compared to other two culture. This is spent media from Enterobacter cloacae and the co-culture. And this is the another thing we observed with the distillery effluent. By the same culture, we find that acidogenic mixed consortia gives a better result, about 69.6% energy recovery that we get in the form of methane if we pass through the methanogenic process. Now, in conclusion, I want to say that biohydrogen production process should be through the biological route will be the attractive by considering the followings, because hydrogen production as such, biohydrogen production as such may not be attractive, but if you combine with the biomethanation process, obviously it has very high potentiality, what you call biohydrogen process. The organic waste are unsuitable as substrate, mainly used mainly due to the complex nature and lack of micronutrient. So agricultural, processing, industrial residue, and distillery effluents are suitable for biohydrogen production. I was talking about the dual cake was prepared to be the most promising as the nutrient supplement for the hydrogen production media, for increasing the overall hydrogen yield and decrease the production cost. Biohydrogen is very promising for the high energy recovery from the organic waste. So this I want to share this. This is very important. And couple of books we already written, and this has been published by first book we have written on biohydrogen production fundamentals and technology advances. This published by CRC Press. I told you Biohydrogen, we published by the Penn Stanford Company and publisher, and this is the first book in the world on biohydrogen. And recently we published another book that is Fundamentals of Biofuel Production Process, different kind of biofuel. If the student want to have the total scenery that how different biofuels can be produced, and we have written in a very compact form. So this is published by CRC Press. Besides that, I edited 2 books. One is Algal Biorefinery and Integrated Approach, and another by Microbial Fuel Cell, the convert waste to what. And this book was published by the Springer. This also a lot of different scientists working across the globe. They shared their experiences with us. So this is a very informative book. If any student interested, they can have a look on that. And I am thankful to all my sponsors, that is particularly Department of Biotechnology, and whose funding is the seed funding that for starting the hydrogen research at IIT Kharagpur, and then Ministry of New and Energy Renewable Energy Sources. They help us for scaling up of the process. The Defense Research and Development Organization, DRDO, they have also giving a lot of fund, and Department of Science and Technology, they help us for establish the one both in the national and international collaboration program, and National Science Foundation that help us because we have a collaborative project with University of Miami, and that is funded by the National Science Foundation, and we are also grateful to that. They also, we have an exchange program of this, and major collaborating institute we have University of Miami, then Oslo University, Uppsala University, Denmark Technical University, Ruhr University, IICT, Hyderabad, then TERI, and JNTU. I told you that JNTU, Hema Bindu was very much associated with us. And this is all my students who contributed. This is a different student contributed in hydrogen research, and also later they also did some work on methanation process. And this is here some of the students already graduated, and some of the students they remain with me, and this is our department. And this is our institute, and IIT Kharagpur doesn't require an introduction. This is the first IIT in India, and it was so successful. That is why we have 23 IIT now. And our students, they bring a lot of name for our country. Thank you very much for the organizer to give me an opportunity to share our that experiences that we have on the biohydrogen production process. Thank you very much.
Thank you very much, sir. Yes, madam.
Thank you, sir. Total hydrogen energy work you have presented.
Yes.
Hello.
Yes, yes.
Yeah. It was so for even to start youngsters, it is very much useful for their understanding and then to pursue in this line, I think. I hope the students will get benefit out of this, and then we have learned so much, and that the pilot project is useful for the industry to take it up for their further implementation.
Yes, yes.
So, yeah. So we will ask the Hyderabad industries also can have a look in that. You have mentioned that website, and we can show it to them. So thank you very much, sir, for your accepting our invitation and then delivering your lecture. Thank you very much, sir.
Thank you. Thank you very much. If any participant have any question, they
yeah.
can
Now Ravi Verma will read the questions, sir. So they have posted in the chat box.
Okay.
So he will read.
Okay.
Yeah.
Thank you, Bindu madam. Good afternoon, sir.
Yes.
There's A few questions from our participants. They have
Yes.
been typing in the chat section, which I will read out.
Okay.
One, Mr. Tyagi is asking, if we are performing acid hydrolysis of biomass,
Hmm.
followed by enzymatic hydrolysis, then what do you think about the selectivity of the hydrocarbons? Will this process fall under carbon-carbon neutral process?
I think the question is regarding the use of lignocellulosic biomass, and for the degradation of the lignocellulosic biomass, the acid hydrolysis is a kind of old process that is already a lot of group has been performed that. And enzymes has both are hydrolysis process, because enzyme we use different type of enzymes for the carrying out the degradation of cellulose, hemicellulose. That degradation we use. Acid also performs this. Now major issue that we have with the lignocellulosic biomass is the delignification process. First, we shall have to remove the lignin, because lignin makes a barrier across the cellulose and cellulose molecule. So until unless you remove the lignin, that cellulose cannot be utilized by the microorganism. So or so that is the major issue. So the delignification needs to be taken care first, and then if we go for the acid hydrolysis, or you compared with enzymatic hydrolysis and combination of these together, we can try to find out that which combination will give the better results. But it's still, this is under research, because no conclusion has been drawn so far. And different group, because different type of biomass are available, and different type of biomass has different amount of lignin content, different amount of cellulose content, different amount of hemicellulose content. So that so again you have to find out that which biomass you are talking about, and you target that biomass, and with respect to that you have to find out what process will be suitable for degradation of your cellulose or hemicellulose material for deriving some useful product.
Thank you, sir. So one, Mr. Munna is asking, when you have converted to pilot scale, were there any major challenges from lab to pilot scale? And is it cost effective to use in a commercial level?
I think this is also a very valid question and very good question. That there are a lot of challenges, because let me tell you that that Himabindu might be knowing that that those who are working with the biological system, they know that to work with a pilot plant is very difficult as far as academic institution is concerned, because it can be done in the industry very easily, but academic institution is very difficult, because in the industry we have skilled labor, but in the academics we have students only, and hardly we have one or two project assistants. They are not skilled labor. So that naturally that challenges we have, that is the group of work of the student. So I am very much thankful to my students. They form a very the commendable job, and they work in a group, and we work in different shifts to run this system. So we have different issues here. We have, first you have to prepare the culture, then you have to prepare the media, then you have to analyze the different sample time to time. You have to monitor everything. And another major issue of this is the hydrogen gas, because since in IIT Kharagpur I could not find any kind of hydrogen user, so I vent out this gas. And for venting out gas also, I have some kind of fire arrestor at the exit point, because hydrogen, if you burn, again it get hazard to my plant. So I put a fire arrestor at the hit point so that it not cause any kind of damage to the process. But that I consider that but the major challenge is your microorganism should be inoculated at the log phase, either in between mid log to late log phase. Now, if you inoculate in the stationary phase, you will not get the good results. So you have to be very much careful when you are inoculating the microorganism. The microorganism when you inoculate, when it should be very active. Otherwise, one may not get the good results. So those are the challenge, and plus you have to maintain the sterility of the pipeline time to time by using steam. We have some PID controller, and through PID controller we control different valves and other things. So those also you have to check time to time whether the valves or pumps they are working properly or not, because those are the challenges that we have.
Thank you, sir. One final question, sir, from Mr. Pramod Yadav. He's asking, are there any application of nanotechnology for converting biomass to fuel?
Obviously, nanotechnology has greater role to play in the energy sector, but particularly we have studied a little bit on that microbial fuel cell, but not in this biohydrogen production process, because obviously we find that where the involvement of the catalyst, some catalytic process is there, where the nanoparticle can play a very important role. So in our process mostly it is microbial process, and we didn't study with some kind of nanoparticles, but at the same time we use the microbial fuel cell by using different type of electrode. There we use some kind of effect of nanoparticles on that particular electrochemical process. There we find some improvement of the conversion process. Hello. Hello. Can you hear me?
Hello. Hello, Ravi Garu. Hello. Oh, his thing. So can you read Sushma other questions?
Yes, ma'am.
Yeah.
Sir, one Pravat Kumar sir is asking, what is the potential of biohydrogen right now?
It has tremendous potential, because that because the industry they are desperately looking for that. That is why the Dhampur sugar mills has taken my process, and they have already this biomethanation process, because anaerobic digestion process they have already, and they have very big unit. 10,000 cubic meter. You can see the volume, 10,000 cubic meter reactor they have. So naturally that. And we know the biomethanation process is a slow process as compared to our hydrogen generation process. Hydrogen generation process is very less. So they are desperately looking at hydrogen generation and the methane formation. So and hydrogen has, I already told that IOC, they have hydrogen filling station. They have a couple of hydrogen filling station in the Dehradun. So they are using, and also already Tata Motors, they have built up the buses and vehicles, particularly Mahindra and Mahindra. They have come up with 3-wheeler and 2-wheeler, and also some international company, they are also coming with a 4-wheeler. So all these things hydrogen can be used. And this because hydrogen production process has the potentiality. The reason is that one way we are treating the organic waste, another way we're generating the hydrogen, and then this hydrogen, if we can use, and it doesn't contain any carbon monoxide and H2S or sulfur dioxide. So since it doesn't contain any carbon monoxide or H2S or sulfur dioxide, so even it passes through the fuel cell, it will not give any kind of problem. Directly, it can generate the electricity. So in that way, this hydrogen, because if you consider the hydrogen production from the coal, that every possibility that coal or some kind of other device, there is every possibility it contains some kind of carbon monoxide, and that causes the catalyst poisoning. So that kind of problem we don't have when we go for the biohydrogen production process. So definitely it has a lot of potentiality, and that is why I told that biohydrogen process, if we can successfully implement in the industrial level, and India will be the first country to do that, because that I am desperately looking for.
Thank you, sir. One more question is there. Electrolysis of water in hydrogen production, is it a renewable source of energy or sustainable method? Because water conservation is the best sustainable practice. How can water usage in the energy production, electrolysis of water in hydrogen production, is it a renewable source of energy or a sustainable method? Because in water conservation, the best sustainable practice. How can water usage in the energy production will be a sustainable method?
I think this is also a very valid question, and Eminari, there is a big research group working on that. That Professor Wayne Srivastava of BHU, he has been doing this for a very long period of time, maybe 20 years that he's working, and he developed some kind of processes, so the electrolysis process for, and I visited his lab. I found that and he also demonstrated that hydrogen, how he can use in the for the operation of three-wheeler, that he demonstrated in BHU. Now let me come back to the hydrolysis process, the industrial level. Now, NICE, there is an organization that is under the seat, that is the sister concern of Eminari, and they have already one pilot scale, that water hydrolysis plant. Now, what problem they are facing? Let me tell you. Problem they are facing, that regarding the life of the electrode. Life of the electrode, they are observing that after some time, that process, that they're facing the life. This is the technology they use, that is not Indian technology. This is the technology they bought from Germany, and they found that after some time, that electrodes giving a lot of problems. So they stopped the operation. They are wanted to go for the bigger pilot plant operation. That hasn't been started yet, but I think 2 days before, I'm in the that advisory committee, that there we have a long discussion, that kind of when they are going to start that, because money already sanctioned 1 year before. They are in pipeline now. Maybe after 1 year or so, they will come up with some kind of suggestion that how it will be good for future aspects. Because at the present moment, the water hydrolysis is not very promising. Maybe at the present moment, maybe the coal gasification and other technique is much better as compared to the water hydrolysis process, because obviously 2/3 of the earth is water. If we can hydrolyze the water and produce hydrogen, nothing like that. But that operational problem of the system, that should be overcome. And if we can overcome the operational problem, then the process can be taken in the commercial scale.
Thank you, sir. There is a last question. Sir, please throw some light on impact of silica on biohydrogen process from rice straw.
Your question is that effect of light on silica.
Yes, sir. Impact of silica on biohydrogen process from rice straw.
Uh, this we have not studied. This we have not studied. That obviously we have used that silica, particularly rice husk, as a solid matrix for our microorganism for immobilization of the solid matrix. But in some organisms we get the good results, and some organisms we don't get the good results. So it will vary from organism to organism. But we didn't study the effect of silica, how the silica influence the growth and metabolism of that particular organism. That way, I know that rice husk contain good quality of silica, which is usually recommended for the chips making industry, but we have not studied.
Thank you, sir. As of now, this is the last question.
Hello. Hello. Sir, thank you very much, sir,
Thank you.
for your
Thank
time.
you.
So, now I will invite Dr. Venkat Mohan, sir. Hello. Sir, are you online?
Yes, madam. I am online.
Okay, okay. So now I invite Dr. Venkat Mohan from IICT for sharing his lecture. And I request Sushma, please introduce.
Yes, ma'am. Good afternoon, one and all. Good afternoon, sir. Dr. S. Venkat Mohan is a senior principal scientist at Bioengineering and Environmental Sciences Lab, CSIR, IICT, Hyderabad. Sir has developed novel and sustainable technologies by the utilization of waste as the potential resource for both value addition and its treatment through multidisciplinary approach. Sir has authored more than 320 research articles and has more than 9 patents. Sir is the recipient of Shanti Swarup Bhatnagar Award. Sir, I welcome you at this platform for presenting your presentation. Thank you, sir.
Thank you very much. Please share. I am not able to share my presentation.
Yes, sir. Yes, sir. One second. I'm making the co-host.
Yeah.
Now you can share your presentation, sir.
Okay. So now you are able to see my presentation? Are you able to see my presentation?
No, sir.
No.
Now it is visible, sir.
Okay. Thank you very much for a nice introduction. Very good afternoon to all. First, I would like to thank Professor Himabindu for giving me this opportunity to share my work on biorefineries with relevant to biofuels, particularly in this webinar. So I would like to present what we are doing in IICT for past 15 years, specifically on developing waste biorefinery systems with the circular mode approach in order to extract resources, particularly carbon, to the maximum extent, which accounts again for circular economy. So I'm from Indian Institute of Chemical Technology, where we work on advanced wastewater treatment systems, particularly related to chemical-based waste management. Apart from that, we also work on biological routes, particularly towards resource recovery from waste in a circular mode approach. For that, we used to have systems which can work with acidogenesis, bioelectrogenesis, photosynthesis, and bioanoxygenesis. And I would like to explain that briefly. How can we integrate all these systems in a loop in order to maximize the resource recovery in coming slides? So the presentation, I would like to introduce some of the facts about energy and fuels, and then discuss a little bit on linear versus circular economy. Try to account why waste is a potential feedstock to next generation, and try to briefly go with the biorefineries and bioeconomy, and discuss 3 of the enabling technologies which we are working at IICT, and close the presentation with biorefinery models. So starting with this slide on energy, everybody know that we are dependent on fossils for our energy needs since industrialization, particularly after 1950. You can look into this graph where exponential increase in consumption of fossils was there for our energy requirement. So with this present consumption pattern, the fossils will not be available for future generation after 2050. So we have to search for alternative feedstocks, which is very important, that can support our energy requirement. Apart from that, we also have to address the global climate issues that is happening because of fossil consumption. So here, in order to convert to renewable sources, that is one of the major issue apart from energy efficiency. At present, we are at 15% of renewables, particularly in Indian context, which again accounts for mostly for wind, and next comes solar as well as hydro. But waste to energy is very little, particularly when we look into the spectrum. So, but India has huge potential to use biopower. Particularly, we have about 22.5 gigawatt capacity of power generation, but at present we are only using to 25 to 30% as per MNRE records. So, however, when we look into the renewable energy in world consumption pattern also, it is also more or less similar. About 15% is renewables apart from other fossils. Again, the spectrum of energy with respect to fossils and renewable will vary from country to country, and their policy as well as their resources which is available in their places. So and not only for energy, I would like to show this slide which I have taken from US DOE. Not only for energy, but for all our material requirement, particularly which right now we are using. Everything we are sourcing from fossil-based feedstock. You can see the petroleum, natural gas lines, red and blue, going everywhere in order to make the materials right now which we are using. So this is a kind of linear fossil-based economy. Either for energy or materials, we are dependent on fossils. And these fossils are very finite in nature and cannot be available after 2050 with the present consumption capacity. And the exponential growth cannot be sustained in this finite ecosystem. And increasing the population in future will have a lot of stress on these finite resources for our material as well as energy requirement. So I would like to mention here about urban environment, particularly with respect to urban metabolism. When we look into the cities, basically cities accounts for 80% of GDP and 75% of global consumption of materials as well as 70% of global emissions. So this is a huge particularly. So again, the materials which are sourced from external environment will come into the city in the form of materials, water or energy or fuel, and it will be utilized in the system, and few of it will be consumed and some of it will be become a stock in the city itself, and little bit is recycled and mostly goes as a waste in the form of emissions or water or wastewater. So useful material, particularly with reference to the either in the form of fossils, we are after utilizing, even though it has value, we are sending it as waste. So we are at present, particularly in urban environment, in a metabolic disorder way with respect to materials, and we are wasting the materials, and a lot of destructive material flow is there, which have a potential stress on the environment, which right now we are looking. So when we look into the materials particularly, we have two kinds of materials, biological and technical. Technical material is nothing but metals, plastics, construction materials, glass we are using right now for our requirement, which after utility, after stocking will come as a technical waste, which can be recycled back. At present, we are sending it to landfills, even though it has value. But biological is very important material here, which is accounts for agriculture, food, wood, fiber, dairy, and livestock, which after consumption in urban ecosystem will come as a biological waste or emission, still which it have lot of value in the form of carbon, nitrogen, phosphate, and potassium. and that can be recovered back by biological routes or integrated biological and chemical routes. But right now we are most of the material we are sending it to landfills. So even though it has value, we are sending it to the landfills. So this is a very critical issue which need to be addressed, and we have to close the loops, which I will discuss in next slide. So just to show you some figures which I have taken from our world data with respect to emissions. The global emissions, basically most is due to carbon dioxide emissions. About 76% attributes to carbon dioxide, among which 65% is for as energy usage and industrialization, industrial process, and about 11% is from land use pattern and forest. The next thing is about 16% for methane emissions, 6 for nitrous oxide, and chlorine has 2%, reduced significantly because of replacement of the refrigerator chemicals. So when we again split these carbon emissions, we can see here global carbon emissions, particularly from energy and transportation sector, it is contributing 55% of the emissions, which can be reduced significantly by energy efficiency means or as well as by replacing with renewable energy. But this 45% attributes from industry.
Hello, sir. Your sound is going low and again. Your sound, sir. That
Yeah, okay. I will speak loud, madam. Now it's fine.
Now it's fine.
Yeah. Okay. So the other 45%, which is very important, particularly 24% is attributed to the food-induced emissions, starting from agriculture to harvesting to consumer and wastage. And again, in this 20%, about 10% attributes to food waste. 1/3 of food which is being produced is becoming a waste. So here 24% is very significant compared to other emissions, which we have in our hand to convert it recycling it back to the environment without any harmful effect. So now we are in the linear economy. Linear economy means take, make, and dispose. Particularly, it's a cradle to grave extractive industry models, which we are practicing since industrialization from 200 years. So according to estimate from European Union, there will be about 15 tons of resources per capita per year consumption. But among these, about 5 tons gets wasted. And among 5 tons, about 60% will go to landfill. So we are wasting about 60% of material still, which has value. So this is creating significant issues apart from depleting the fossils. We have all environmental issues, health issues, many resource recovery, and many things are there. So this we cannot sustain. We have to move. Particularly when we look into some of the figures I try to put here. So domestic material consumption global, it's about 40 billion tons per year as per 2010 records, accounts for 5 to 27 tons per person per year, where 10 tons per person per year is the average, global average. So it depends again on the low income and high income country, where 5 is from low income country, 27 is from high income country. This is according to 2010 figures and according to the linear model. But by 2050, with the same consumption pattern, we will be like a DMC will rise up to 90 to 180 billion tons per year, which accounts for 88 to 17 tons per year per increment in population, global population from 7.8 billions to near 10 billions, and India accounts for 18% of the global population. Here, if we continue to live like this and consume like this, by 2050, we require 3 times more resources, a lot of stress on finite resources, and 50% more fuel, and 70% more of food, fiber, and feed, apart from 50% more water. So this again adds to 70% of people by 2050 will live in cities. So cities again contributes to 70% of global emissions, 50% of global water. So cities will be the major issue in coming future 10 to 20 years to make it more environmentally amenable. Otherwise, it will create a lot of global environment issues apart from fossil resource. That's why SDG goal 12 represent responsible consumption and production, which is very important, and this accounts mostly for circular economy. Particularly, we have to move from linear to circular economy. Otherwise, there is no alternative route in order to convert the resource or reuse resource recovery means which we have to practice. Basically, when we look into the circular economy, it depends on 3 pillars. One is we have to design the waste as per the format that waste should not be a waste after its primary process. It should be a feedstock for other process so that it can be continuously used for one purpose or other purpose. That will make it utility, maximize its resource recovery, like movement in the system. So nothing will be wasted, very little will be wasted. So always material will be in circulation. So that will reduce stress on the finite resources. So this kind of design is very important, and that makes keep material in use. And moreover, the biological material, regenerative natural system is important factor, which will have significant role to convert resources back into the environment. So that is nothing but bio-based economy, where biological routes and hybrid biological thermal or chemical routes will be used to convert the useful material present in waste into some products that can be primarily used either for fuels or products. So bioeconomy and the circular economy, circular based bioeconomy will have a significant scope in coming years in order to in order to make the resources more recoverable and reusable in the system. So when we want to go with the circular economy, we have to discuss a little bit on the resources. Particularly, waste is the major resources in the present scenario. Particularly, the waste is not a waste as it has a significant amount of resources. We have 4 different kinds of waste, which is available in huge quantities. Particularly, when we look into the municipal solid waste. Basically, we have about 150,000 tons per day as per Ministry of House and Urban Affairs recent figures, which accounts for significant amount of energy. And mostly right now, more than 80% is going for landfills. And the basic advantage with Indian waste is more than 50% it is biodegradable, which can be easily converted into value-added products. Apart from that, we have huge amount of sewage, about 30 billion liters of sewage generated in India per day, which again accounts for huge amount of energy as well as a source for nutrients, particularly nitrogen, phosphorus, and potash, which is again fossil-based chemicals, particularly potassium and phosphorus. So this is also a very important feedstock, particularly that can be recirculated back. Apart from that, we have huge amount of fecal sludge, which has potential carbon and nutrient source apart from industrial wastewater. And there is no depth of material. Every year there will be increment of 10% in municipal solid waste because of our increase in population and our economic improvement. So there is no depth. Every year there will be 10% increment. And so far we are only using about 4% of waste to energy potential. So when basically we have waste, we have to go for biological treatment as per the regulatory requirement. Biological treatment is always very sustainable because it doesn't produce any harmful byproducts that can again create problem to the environment. So basically we have 2 kinds of process, aerobic and anaerobic. Aerobic process is an energy intensive process where oxygen will require to convert carbon by aerobic bacteria to CO2, H2O as well as new cells. So alternatively, we have a versatile process, anaerobic process, which is a very mature process, energy giving process, I would like to say. Methanogenesis, everybody know that this is a process which was there for almost 100 years in the starting from gobar gas right now to anaerobic biodigesters, which is producing methane, biogas. But still we can retweak this process towards other value-added products. We can regulate the metabolism towards acidogenesis to produce hydrogen as a terminal end product, or in a defined fuel cell, we can produce bioelectricity, or in oxygenesis, we can produce bioplastics, or using solventogenesis conditions, we can produce solvents. Or apart from bacteria, if you can use microalgae, by mixotropic mode of cultivation, the algae can take carbon from organic carbon as well as inorganic carbon and convert into biomass, which can be again used into multiple products. So there are huge scope, particularly with biological convert the carbon and nutrients into potential feedstocks. So as I told that waste is not a waste because it has huge amount of nutrients in the form of carbon, which represent by COD from about 500 mg per liter to domestic sewage to more than lakh in the case of chemical as well as distillery wastewater. Apart from that, it has good amount of nitrogen phosphate. All these three elements will form an important feedstock for any biological process to work out. So when we have a solid waste, again, basically right now we are sending it for landfills mostly, a little bit for composting, which is very important process, and little bit for incineration, a little bit for digestion, but it also have potential to convert into chemicals because huge amount of solid waste, biodegradable nature, and can potentially produce platform chemicals as energy. So that way we can reduce greenhouse emissions as well as recovery efficiency we can increase. So solid waste and wastewater are potential feedstock, I would like to say. And this figure just to represent any kind of wastewater, including domestic, industrial, and solid waste, we can, or including gases, we can convert into biological to bioproducts by using biological process, versatile biological process, basically starting with anaerobic digestion to methane, which have huge potential applications as bio-based materials apart from remediation. There's a huge scope particularly we can look at. So coming to the waste, again, I would like to say that waste is not a waste. As yesterday, some of the guest of honor, he told that USA people are changing the name from treatment plants to resource recovery centers or as biofactories. In future, in another 10 to 15 years of time, wastewater treatment plants will become biofactories, which convert resources, resource recovery centers. So the perspective of wastewater treatment will significantly change in coming years because they are potential feedstock for many of the chemicals and energy. So to happen all these, we need to have technologies. At present, we have a couple of technologies which are viable, that is anaerobic digestion, which can produce methane, and composting, which we recover the source and we can send it to, again, agriculture to close the loops. However, we need many of the technologies because methane production still has its own disadvantages, as methane is 24 times more potential than CO2 as global warming gas. So apart from that, going to methane at the terminal point, we are losing a lot of chemicals. We are converting CO2 as well as methane. So in between intermediate point, we can get a lot of chemicals properly regulating the process. So in this direction, I would like to show this slide where you can see different lines coming from glucose. I would like to say here, anaerobic process is a very versatile process, versatile biofactory. We can treat the process as we require by giving 6 carbon rings, glucose primarily, and we can treat the process either to produce lactic acid, lipids, conventionally to methane or butanol or propionate, ethanol, like that. There is a versatile platform, I would like to say, in any biorefinery system, particularly waste-based biorefinery system. Anaerobic process will be the primary process in order to simplify the complex molecules of waste to some intermediate products or to the final product. So as 15 years back, we started working on biohydrogen production, similar to Professor Himabindu, as well as Professor Das. So because hydrogen economy is very important thing which will be coming in near future. Already some of the countries in European Union, they are trying to convert to hydrogen economy. So looping hydrogen into their value added chain or transportation systems because hydrogen is a clean gas and and doesn't have any global warming potential. So we started working on that hydrogen production from 2006, and similar to Kharagpur with the same project, Ministry of New and Renewable Energy, we tried to set up a pilot plant in IICT campus with 10 million cube capacity. And then subsequently with the funding of CSRA, in order to recover resource recovery efficiency, increase the efficiency, we designed a waste biorefinery facility and tried to maximize the resource recovery by 2007. This I will explain in coming slides. So basically, I will not go into deep about hydrogen because Professor Das already has given a very detailed presentation. But I would like to say a few words here. Like our basic objective is to use wastewater as a feedstock and mixed culture as a biocatalyst. So these two things are the basic things, because we want to convert the anaerobic digesters that at present producing methane to produce hydrogen as a terminal product. So here metabolic regulation is very important phenomena. Only I will discuss about that one. And these are some of the challenges which we try to resolve before going to the pilot plant. The major problem is when we are using a mixed culture, we have coexistence of methanogenic bacteria, which will create a lot of problem because it reduces the productivity rate of hydrogen and also increase slowly methane production. And another major issue is regarding the fermentation inhibition because of fat acid formation along with hydrogen, which reduce the redox condition towards acid side, and production efficiency will get reduced. And because of that, low substrate conversion efficiency will be there. Again, wastewater, when we are using, the load and composition will have a significant influence on the production rate. And the fourth one is the wastewater coming from hydrogen reactor still has 50% of COD, which needs to be treated as per the regulatory requirement. And economics is again an issue apart from purification, storage, and transport. So I would like to explain how we try to selectively enrich the estrogenic bacteria, which is very critical when we are using a mixed culture. We try to use the standard like classical microbial techniques such as shock-based techniques, which will help to make the estrogenic bacteria, which are spore-forming bacteria, goes into sporulation, and the methanogenic bacteria, which cannot sustain shock loads, get inhibited. So these strategies we try to use and then studied for a quite long time, about 1 year with 250 cycles in different reactors to study the microbial diversity. So the untreated inoculum during zero time, it is about 51% of firmicutes, which are hydrogen producing bacteria or acidogenesis, has a diversity of other groups of bacteria. But when we give different shock loads at the end of 1 year, we observed the selective enrichment of estrogenic bacteria, the firmicutes. So this has shown a good lead to how to design a pilot plant, which we have done in design operating of the pilot plant. These are some of the bioreactors which we have used, and the PI and diagram of 10 meter cube pilot scale system and photograph of the system where different unit operations we try to selectively enrich the bacteria and to regulate the methanogenic bacteria, particularly to suppress the methanogenic bacteria. During operation, we have a specific patented process. So this produced about 50,000 liters of hydrogen per day by using biogenic municipal waste, basically food waste. So any process when we are looking into the new process, which is before going to the market, the sustainability analysis is very important compared to the existing process. Like otherwise, now in coming days, any process will not go into the market. So one of the thing is that we can do by life cycle assessment, basically taking into the standard protocols given by ISO. So we try to take the hydrogen production process by biological means and try to compare with other 3 processes which is right now existing with basically with using fossils, particularly natural gas, and categorized into 4 damage categories like human health, ecosystem quality, resources, and climate change. You can see that the green one represents the biological hydrogen production process, and other 3 are fossil-based hydrogen production process. Compared to green one, other 3 has a higher human health impact, and the climate change is negative in biohydrogen.
The variation is there in the voice.
Voice, madam?
It is not
Okay.
constant. Some variations we are observing. So.
Okay. So if I can speak loudly, is it okay?
Yes.
So I will speak very loud because I don't have internet. Some problem is there, so I am working operating with hotspot. That might be the problem.
Some
So,
variation. And
yeah, yeah.
okay.
Yesterday there was rain, so my actual
Because
that thing got so that might be the problem, madam. I will speak loudly and try to finish as soon as possible so that it will not be. So climate change, it was negative, particularly there is no negative impact on because of biological hydrogen production process, but other three processes has significant climate change. And similarly, this process is not using any resources. So it's again negative side. This is they are using the resources, fossil resources, so it has impact. Likewise, ecosystem quality, it has a very good quality, but other three doesn't have so much good impact, particularly on ecosystem. Because so this shows the sustainability of biological hydrogen production process. Basically, because we are taking waste as a feedstock, so a lot of reduction in climate issue as well as resource. So likewise, sustainability analysis also shows that biological process has a significant impact. So this, so then when economics will come into picture, when we are going to the industry. So basically, the hydrogen production cost with our process, it is coming about 200 rupees per kg. So the market cost varies between 100 to 150. So we cannot compete with the market because of the cost at present with the production process. So then we try to study the side stream valorization, which helped us to reduce cost of hydrogen production significantly. So as I told, the outlet from hydrogen reactor, it has still 50% of the carbon source, which can be looped to other process to produce second product, either in the form of hydrogen or methane by methanogenic process, or to anoxic bacteria to convert the fatty acids to bioplastics, or it can be used for organic farming or for biodiesel production by microalgae, where fatty acids will be good feedstock for mixotrophic of cultivation, or in a microbial fuel cell where it can produce bioelectricity, or with the photofermentation process hydrogen. So by way, we can convert the 80% of carbon, we can get two forms of the products. This is the concept where biorefinery coming to picture, side stream valorization. So this helps us to reduce the cost of production cost of hydrogen. And at the same time, we can also address the environmental issue by 50% of carbon, which is coming still from hydrogen reactor, that we cannot send it without treatment. Apart from that, we are trying to convert into some useful product, bio-based product. So this is important strategy, which will be coming up and will have a long standing, particularly circular economy. So here I would like to mention about bioethane, which Professor Das also has discussed. But the basic advantage here is bioethane has a lot of flexibility, because 10 to 15% of addition of hydrogen in the name of HCNG. Right now, Petroleum Ministry of Road and Transport, last month, it has kept this as an important transportation fuel. Without changing any engine, we can use this fuel. So likewise, if we want to use hydrogen for transportation, we required a specific engine or a fuel cell to convert into energy. But supplementing 10 to 15% with compressed natural gas, the capacity of the system can be increased, efficiency can be increased. At the same time, we can reduce the reduce the emissions. So bioethane is a very important entity in this direction. The second one I would like to say, bioplastics. The bioplastic conversion, 80% carbon conversion into polyhydroxyalkylate, which will have significant role to play in packing or in medical thing. This is again important product which can be integrated with hydrogen production process, or we can use it as a phosphate solubilizing agent by 10% of supplementation in water, so that it can increase the availability of phosphate, soil-based phosphate to roots, and can increase the growth productivity. So organic farming. And another, the last product which we are significantly working is trying to work on carboxylic acid. Along with hydrogen, volatile fatty acids will be the major feedstock, the major byproduct which is coming. So we try to take this lead and try to produce more of fatty acids in the form of acetic acid, butyric acid, or propionic acid. Apart from this, we also get hydrogen. Now, these have more market value. These are the primary products trying to increase the productivity. At the same time, we'll be getting hydrogen, which is again a byproduct. And by integration of these two, we can get a reasonably good economic viability to sustain in the market. Likewise, there are significant potential, particularly starting with osteogenesis. In a biorefinery approach, we have significant routes to go with, which can be looped and can be optimized. So second process I would like to say is we are working on microbial fuel cell, microbial electrochemical technology, very versatile process and important platform, even though with energy conversion, even though it has still limitations, but it has very significant other applications, which I would like to discuss. So very much similar to hydrogen production process where we put electrodes, anode and cathode, separated by proton exchange membrane, same bacteria, same wastewater, produce proton and electrons along with CO2. The proton will pass the proton exchange membrane to cathode, electron through anode, passes to the resistance, and in cathode chamber, proton and electron combines along with oxygen to form into H2O. So because of this, there will be cell EMF, which is nothing but electricity. So basically 1 kg of COD produces about 170 watts of energy, but at present, it is only 20%. So I would like to say that 1 mole of glucose, we can produce 24 protons and 24 electrons. So however, these technologies started way back in 2000 to 2005 by basically using it for wastewater treatment as a microbial fuel cell. But during these 15 years, it has diversified into different applications, which have significant role to play in bioenergy spectrum as well as bio-based economy. It can take any kind of wastewater from domestic effluent to industrial effluent or CO2 or saline wastewater, and based on requirement of byproduct, either MFC for power or bioelectrochemical treatment for only for treatment or recovery of nutrients. BES converts CO2 to some value-added products. Microbial electrolytic cell with little input of energy, we can produce hydrogen from waste, and microbial desalination cell can take saline water and treat the saline water. So all these applications make it a very important platform technology, which has a emerging future in coming generation, coming 10 to 20 years. So these are the fuel cells which we used. The stacking of fuel cells is very much important to accumulate the power. Start with H type of fuel cells, and then we have removed the membrane. Then we try to make it into different stacks so that we can accumulate the power. This is one of the stack continuous mode of sewage operation, about 8 systems which can produce about more than 1 watts per meter square of energy continuously. So likewise, there are many applications, particularly with MFC. Different, we can use like solid phase MFC fuel cells, or we can use the root zones to convert energy as well as to increase the productivity of plant, or we can use in soil itself to make bioremediation as well as phytoremediation. Likewise, many applications, but still when we look into the microbial fuel cell with respect to energy generation, it has a lot of challenges still exist to scale up before scaling up. Like some of these things like electron, we are significantly losing the electrons. Biocatalyst is important thing. Economics with respect to membrane and electrode is one of the important thing, and as well as composition. And we try to do some of the optimization studies before scaling up to address particularly with respect to wastewater systems, which I will not go into deep because of lack of time. The important application MFC, apart from power generation, I would like to say it's a bioelectrochemical system, particularly with respect to biorefineries. So it can use as a pre-treatment system before any of the biological process, either anaerobic digestion or biohydrogen production process. The pre-treatment will help to reduce the complexity of wastewater composition so that that can be easily taken up by bacteria for production of either hydrogen or methane. So it works as a a very good pretreatment system with little input of energy or without inputting of energy by closed circuit mode of operation. Likewise, we try to use for solid waste, which increase the availability of carbon for subsequent process in acetogenic fermentation for fatty acid production. Or we also used with sludge with a little bit of pre-treatment and subsequent process. We are trying to convert it into chemicals in the form of fatty acids, hydrogen and steroid. Likewise, by little bit input of energy in a form of microbial electrolysis cell, we can convert carbon into hydrogen, or we can regulate the electrofermentation process towards by a system, a defined system. We can input energy, little bit input of energy. The fermentation, as everybody know that it has its own limitations, we can regulate this process towards the requirement of our product, or we can increase the rate of fermentation. That we have applied a acetogenic process to convert into fatty acids, significant increment in biogas production, as well as significant productivity with respect to VFA was observed at lower organic loading rates. So apart from specific diversity enrichment, which is required for this purpose. And we also can use this microbial fuel cell to upgrade the hydrogen production, where this has advantage to convert CO2 to methane again by the specific bacterial group. So we can increase the productivity fraction of methane in total biogas production to 10 to 15%, so that the CO2 emissions can be reduced. Or we can use the CO2 in a two-chamber system, a cathode chamber, to convert it into fatty acids, particularly by using the advantage of anode chamber. Here in cathode chamber, homoestrogenic bacteria will be there. It will convert the CO2 in the form of bicarbonate to fatty acids. So this is again a very important thing which right now European Union as well as IOCL is looking into. They are working with LanzaTech to make this process to higher scale, practical scale. So we are trying to increase the productivity, because taking CO2 to aqueous phase and then converting has its own limitations, and it also requires a certain kind of bacteria and condition. So right now we are trying to increase the productivity so that it should be economically viable. Like that, bioelectrochemical systems, particularly MFC, also has significant potential to come up with different products, including succinate, caprate, butanol. So this can also be looped into biorefineries in a significant way. The third and last process, I would like to say photosynthesis masonry, which is a life-giving process for all of us, can be also looped significantly in the biorefinery at the terminal point, where the residual carbon source can be looped back into the system by mixotrophic or heterotrophic of cultivation, and then use that biomass for multiple purpose. So this is the sequence of integrations we have done, particularly with hydrogen production, to increase the productivity of biomass. Biomass is important factor here with respect to economics, and we try to do this with lipids production. Now, lipid production increment as well as biomass production will have economic viability. These are the raceway parts which we have constructed in IICT, 3,000 liter 2 raceway parts. And likewise, CO2, particularly photosynthesis, the major feedstock will be CO2, and has a very versatile integrations, which I try to put in this figure, but I will explain in coming slides. So to conclude, I would like to say that waste biorefinery, similar to petroleum biorefinery, is very important emerging technology, which will have significant role to play in circular loop economy as well as bioeconomy in the context of fossil depletion. So in petroleum crude, we'll take the crude and try to use various processes to convert into different processes. Likewise, a waste biorefinery, we will take waste as a feedstock and try to use some biological and chemical or integrated thermal process to convert the resources into some value-added products by closing the loop approach. So with this strategy, in ICT, we try to develop a waste biorefinery platform, which can take either waste or wastewater. Waste after pre-treatment or wastewater initially will go to microbial fuel cell setup, where it will try to reduce the complexity of wastewater or waste, so that it will be more amenable for secondary biological process. This process will reduce 20% of carbon and produce electricity, the first form of energy. And the second reactor converts 60 to 70% of carbon to hydrogen and 2 forms of energy, and 80% of carbon conversion efficiency, 70 to 80. The residual portion will go to the other process, either photohydrogen methanogenesis, bionoxygenous MFC algal cultivation, and produce third form of product, bio-based product. So 3 forms of products and 90% of carbon conversion efficiency, maximizing the resource efficiency, and residual fraction we can treat and reuse in process as and for gardening, so that we can reasonably close the loop and can produce bio-based products. This we try to integrate with hydrogen production process and try to study different loops which will be more feasible for effective resource recovery. It's a closed view of things, 10 meter cube capacity, continuous mode system. It's a terminal process where phytoremediation was taken as advantage to convert to treat the wastewater before looping into the system. So likewise, there are huge, significant potential biorefinery models we can design and keep upon our interest to specific requirements. Particularly, ours is a chemical institute, so we are trying to use waste and try to convert into some primary sugars, renewable sugars, which can go into chemical synthetic routes. So when we are supplementing the total chemical process with renewable sugars or some renewable chemicals, so the total process greenness can be increased. The sustainability of process can be increased. Likewise, we can also use the urban cycle, different cycles which is existing in urban ecosystem, biocycles. Now which are open, we can make into loops so that urban biocycle can be self-sustained. This will be a very emerging area, particularly with respect to smart cities. Or we can use the domestic wastewater to convert into recovery carbon, nitrogen, phosphorus, phosphate, which is an existing process right now, but economic viability still is a question. So we can also design with photosynthetic process at a primary pace. We can design a self-sustainable systems, algal biorefinery models, where primary microalgae cultivation will be there. And after extracting lipid or other chemical, the biomass can be pre-treated and used for other product formation in a circular loop. So that we can close the loop. There is no input of resources except wastewater or sunlight or CO2. We can produce products. This self-sustainable systems right now is very emerging interest, particularly when we look into the space program, where the space systems required self-sustainable loops. They cannot carry all the materials. So this is an emerging area, especially for the coming generations. And similarly, we can design with Ajolla or duckweeds, or we have various models are there, but I will not go into deep. Before closing, I would like to show again this slide. Whatever materials we are producing from taking raw materials from fossils, petroleum and natural gas, we can produce same with biomass and bio-waste, all the materials. So the way of bioeconomy is to supplement to certain extent, reduce the dependency on fossils, so that the fossils can be available for some more time. And at the same time, by using waste feedstocks, we can, when we are converting it to products, we are able to reduce the emissions also. So it is sustainable, and as well as it also addresses circular economy thing. So this kind of interventions are very much required, and it also supports many of the sustainable development goals as such, and has a huge market, particularly independent market. Right now it's very staggered, and this needs to be go with a small scale as well as startup companies. But right now our waste management industry, people from outside the country are trying to take advantage, but we have huge potential to generate green jobs and many of the things, and also support the environment, but still needs a multidisciplinary approach for many of the things to come up to the scale as well as policy. So I would like to thank my students whose work I have presented here, and specifically funding from different funding agencies, MNRE, DBT, DST, as well as European Union, which helped me to do this research. And thank you very much for your kind attention. And I would like to thank Professor Hemabindu for giving me this wonderful opportunity. Thank you. Hello, madam.
Hello, Ravarma Garu, can
Hello.
you read the questions?
Yes, madam. Thank you very much, sir, for that.
Madam.
Sir. Hello.
Audio is okay, na? Oh.
Voice, sir?
Uh,
Is fine. It's fine, sir.
Voice is, yeah, okay.
Voice is
Okay.
fine, sir. Fine.
That's fine, sir.
And for other members also, it's fine. Only for me, I think some problem. Only one participant raised some thing.
Yeah, yeah.
This. Okay.
Thank you very much, sir.
Yeah.
Questions.
Yes, sir. I actually we have been taking questions from participants. They have been typing in the
Yeah,
chat
please.
section, which I would like to read out, sir.
Yeah, please.
So, firstly, Mr. Pawan Kumar is asking, as you discussed the different types of waste to energy, from which type of waste will give us the best energy for present needs?
So basically, when we want bioenergy, the thing is, more the biodegradability is there, the more efficiency it can produce energy. The second thing is organic loading. The load of, if we are taking domestic wastewater, which will have 500 mg per liter of COD, and we have to produce methane, means it's not economically viable. If you are taking distillery wastewater, which have COD of 1,50,000 and has biodegradability more than 0.5%, that can be reasonably good for production of bioenergy. Likewise, it depends, it varies on the composition of waste as well as load of wastewater. So more the organic loading rate, more the biodegradability, more feasible for bioenergy production.
So, any
Yes, sir. And one Mr. Narsimha is asking,
Yeah.
acid or alkali treatment to lignocellulosic waste to produce toxic chemicals like furans and which inhibit the growth of microorganisms. How can we rectify this problem?
So there are two ways. Basically, when we want to separate cellulose, hemicellulose, and lignin, that is a different thing. Though, so there we want to recover the chemicals. So toxicity will not be there. When we want to use it as a feedstock for bioenergy generation, then it will have other things to play, like how we are using. If we are pre-treating, means it's not economically viable. We have to use it is with a pre-hydrolysis step so that the toxicity will not be significant. So at present, using biomass by pre-treatment for any bioenergy generation is not considered as an economically viable technique. But using pre-treatment to convert into chemicals, it has more value. So furans again has a value as a platform chemical in chemical synthetic routes or chemical industry, I would like to say.
Thank you, sir. Next, one Mr. Pravat Kumar is asking, are there any statistics about the current bioelectricity production in India?
As such, there is no scale. So far, there is no scalable system. So everything is at pilot scale. But you can refer the literature that some of the pilot plants were reported from different scales, like 100 liters to 4,000. Particularly with respect to MFC. But hydrogen, there are bigger pilot plants and is amenable for commercial translation. But the basic issue is with respect to policy. It was not mentioned in biofuel policy, recent policy. So it will not give you any kind of these kind of whatever they are getting for bioethanol, some kind of government these things. So that will not be there. So still it needs time to go with hydrogen to commercialization. But MFC still it needs optimization for scaling up.
Thank you, sir. Mr. Sai Chandu is asking, what were the boundary conditions considered during the life cycle analysis study?
So we have considered gate to gate because we don't have information for other fossil based process for cradle to cradle. So we use it gate to gate, and then we try to extend only hydrogen production process from cradle to cradle when we are integrated with waste biorefinery. So that can go with because circular loops are there that we analyzed with cradle to cradle approach.
Thank you, sir. One is Simran Kaur is asking, I'm working on a single chamber MFCs. I believe, sir, your group is working on dual chamber cells. Any specific reason why to go for dual?
Initially, we started with the dual chamber systems, but right now, after quite long time, after 2009, we started with single chambers only for converting into value-added chemicals such as either hydrogen or to convert CO2 into chemicals. We are using dual chamber. For power generation, now we are using single chamber system without membrane and without any catalyzed electrodes. As dual chamber will not work out for power generation, but same time, value-added product recovery will also not be possible with the dual single chamber system. So depends on application, configuration will vary.
Thank you, sir. Sir, I just had one query. Generally, sir, the energy content of municipal solid waste and trying to generate energy from this MSW, when any young startup or entrepreneurs, in what line should they be looking to work, especially this waste to energy?
At present, composting as well as anaerobic digestion is more like it can easily go into the market because it's known to everybody. And so integrating with composting, it will be easy to take up because everybody knows in the system, either administrator or other system, it can easily go into the loop. But when we want to vary, if you want to go with hydrogen and then these chemicals, still it requires some time because it was not so far listed in any of the government policy framework or such that kind of things. So at present, biomethane composting will directly go within no time. In another 1 to 2 years, other things will come.
Thank you, sir. I have no further questions, sir. With that, I thank you once again. Hand over to Bindu, madam.
Hello.
Thank you.
Sir, thank you. Your lecture almost covers with the energy resources, the requirement of alternative energy resources and the piling up of our waste and how to convert that waste into like a refinery approach till the end, how to maximum utilization of that, how to convert into the valuable resources. So it's a wonderful lecture, sir, and I hope all the students will get it. So number of research projects in this one area itself, you can take up a lot of technologies. So it is a good opportunity for them to know about what's going on in this line. And then, so thank you very much for your support, sir, for arranging the other speakers today afternoon, like Dr. Nikhil and Dr. Karthik and tomorrow's guest, Dr. Rashmi, your student. So thank you very much for your support for this webinar. So we'll continue this in future.
It's pleasure. Thank you very much for giving us the opportunity. And I hope it will be it's a very wonderful seminar. Yesterday from inaugural, it was, I enjoyed.
Yeah.
And also I wish the very best to all. Thank you very much.
Thank you, sir.
Thank you.
Thank you. So I request all the participants to join at 2 o'clock. So afternoon speakers are Dr. Nikhil and Dr. Karthik. And hope we'll join by 2 o'clock. Thank you. Thank you, sir.
Thank you. Thank you.
Okay, I request all participants to log back in at few minutes before 2 o'clock. We
Like
will join again.
1:45 onwards, we can
Yes.
reconvene.